Hello, I'm Professor Fernando Toffoli, and I'm going to present the paper entitled Maximum PowerPoint Tracking based on the Curve Sweep Method. The presentation is organized as follows. Section 1 presents some basic principles associated with Maximum PowerPoint Tracking, or MPPT, some basic DC-DC converter topologies used in MPPT applications are described in Section 2. The proposed technique is presented in Section 3. This technique is based on sweeping the whole current versus voltage characteristic of the PV device. The design specifications of a PV system composed of a SEPIC converter are given in Section 4. Simulation and experimental results are provided and discussed to validate the theoretical assumptions, and the main conclusions are given in Section 7. Photovoltaic solar energy stands out as an interesting alternative for the diversification of the energy matrix and for promoting the dissemination of distributed generation. It has also great potential for mitigating the dependency on large generation centers. However, it is well known that PV devices present a nonlinear characteristic curve in terms of the current versus voltage and power versus voltage curves. Besides, there is a single point in the characteristic curve in which the extracted power is maximal. In other words, it is necessary to ensure that the PV system is capable of operating at the maximum power point condition, considering the high cost of PV devices and the low conversion efficiency. It is possible to implement MPPT techniques based on the monitoring of voltage or current of the PV device. In practice, voltage-based approaches are more often employed because of low implementation complexity and use of simple voltage sensors like voltage divisors. The literature presents a plethora of solutions for achieving MPPT. Possibly, PNO and INC are two of the most popular solutions which allow determining the maximum power point. However, both techniques present some limitations in special conditions. The techniques present poor performance when fast variations occur in the climatic conditions. This may lead to the oscillatory behavior of the extracted power and reduction of the efficiency. Besides, both techniques may be trapped around a local maximum when partial shading comes to occur. Thus, it may not be possible to determine the global maximum power point accurately. Several converter topologies can be used for the implementation of MPPT techniques. Possibly the buck and boost converters are the most obvious choice for this purpose among the classical non-isolated DC-DC converters. However, they cannot sweep the entire current versus voltage characteristic as demonstrated in previous works reported in the literature. Thus, only buck-boost type topologies can sweep the entire curve, and therefore a SEPIC converter is adopted in this work because the input voltage source, the switch, and the load are all connected to a same reference node. The input current is continuous, and it is possible to control the short circuit current thanks to the coupling capacitor. As previously mentioned, the proposed technique is based on sweeping the entire current versus voltage characteristic by varying the duty cycle from 0 to 1. For this purpose, it is necessary to measure both the current and voltage of the PV device. The algorithm is responsible for determining the maximum power PMPP as well as the duty cycle DMPP associated with the condition of maximum power. The control system must ensure that the SEPIC converter operates with a duty cycle DMPP so that the maximum power can be extracted. The output power of the PV device is continuously monitored, and if the absolute error E is less than a given value beta imposed by the designer, then the algorithm returns to the beginning of the flowchart. Because of the limited availability of resources in the laboratory, the PV system was implemented for a single 10-watt module KST10T in standard test conditions, or STC. The specifications of the module are presented in the left-hand table, which includes the parameters of the single diode model used in the simulation tests. The specifications of the DC-DC SEPIC converter are provided in the right-hand table, in which a switching frequency of 31.25 kHz was adopted because a simple Arduino microcontroller was used in the tests. These characteristics were obtained with the single diode model provided by PSIM software, only to show that the model can represent the module accurately, and therefore it can be used for any climatic condition in terms of irradiance and operating temperature. Here we have some results for comparing three techniques that are P&O, INC, and the proposed method. A time window of 0.1 second is adopted from the moment that the system is turned on until the maximum power is determined in steady state condition. It is observed that the average power for a time window of 0.1 second is the least for the proposed method because it is necessary to sweep the entire current versus voltage characteristic, which takes longer to achieve the maximum power, unlike P&O and INC. However, both P&O and INC present an oscillatory behavior, as we can see in the provided results. Here we can see simulation results in STC considering a comparison among the three techniques. It is observed that P&O and INC present an oscillatory behavior of the extracted power, and therefore the average value of the maximum power is less than that obtained with the proposed method. It is also observed that the curve sweep method can determine the maximum power accurately without such undesirable oscillatory behavior. Here we have a picture of the experimental setup, which comprises DC power supply, an oscilloscope, and measurement devices. It is worth mentioning that the irradiance levels are varied by using a canvas made of fabric. Several layers of fabric are used to vary the irradiance levels in the performance tests. Besides, the temperature did not vary significantly during the tests. The tests were performed in uncontrolled environmental conditions, and here we have some waveforms for comparing the performance of the techniques. The voltage, the current, and the extracted power were measured with an oscilloscope, and it is observed that the proposed curve sweep method is the one that presents the highest maximum power extracted from the module. Similar tests were performed with varying irradiance conditions, and as shown in this table, the voltage, the current, and the extracted power were measured. The extracted power is also divided by the maximum theoretical power so that the efficiency is calculated for each one of the techniques. It is observed that the proposed technique is the one that presents the highest efficiency for every climatic condition. Dynamical tests were also performed, in which the irradiance is suddenly decreased. As expected, PNO and INC present an oscillatory behavior of the extracted power. This undesirable behavior is not observed in the proposed technique. However, it takes longer to sweep the whole current versus voltage characteristic. Therefore, the resulting efficiency is lower than those obtained with PNO and INC. Every time the climatic condition changes, it is necessary to sweep the curve again. However, the introduced technique can determine the maximum power accurately for any operating condition, including partial shading. This work has presented a simple MPPT technique that can determine the maximum power extracted from PV devices accurately. This technique can overcome the undesirable behavior of PNO and INC when submitted to fast changes in the climatic conditions and partial shading. A possible drawback lies in the fact that it is necessary to sweep the whole characteristic every time the operating conditions change, which may lead to slower dynamic response than the aforementioned techniques. Thus, this is the end of the presentation. Thank you for your attention.